Okay, welcome to 2.3, day 2, second part of continuity here. Okay, so I want you to take a moment and write down this definition of a continuous function. A continuous function is a function that is continuous at every point of its domain. Very important phrase there. Okay, got it? Alright, so here's what we're talking about. This is a function again that you guys should have memorized by now. This is the y equals 1 over x graph, right? And you would think maybe that this is not continuous as a function because of the fact that it has a vertical asymptote for one thing. Alright, so here's the thing though, if you look at the actual domain for this function, it's x cannot equal 0. It's all real numbers except x equals 0, which we can also write as all negative real numbers up to 0, and from 0 to infinity, or we can write as negative infinity, comma 0, and 0, comma infinity. These are all ways of writing the domain. The point is, on these two parts of the domain, the graph itself is continuous. We do have actually a limit for every single point, and actually have points for every point that we decide to take a limit at. So for every point we decide to take a limit at, and for every limit we take, there's a point defined. So we have continuity, at least on the branches. So technically this is a continuous function. It is continuous for the portions of the graph that are meant to be considered. Okay, so that might be kind of a surprising definition. Alright, so why don't you take a moment and look at number 31. Exercise 31. We'll do this together. It's fine. So, alright. Let's take a look here. Okay, explain why the given function is continuous. F of x equals 1 over x minus 3. Okay, well, domain is basically negative infinity up to 3, and 3 to infinity. Should have put my little and symbol in there. Okay, in fact, we know what this graph looks like. This is the same graph, just shifted over a little. Alright, so let's go and draw it. I guess it'd be over here at 3. This is not drawn to scale, but the two curves that we drew there are indeed continuous curves, smooth and continuous there. So we definitely have continuity on those branches, so it's a continuous function. Okay, so we could say the graph is continuous at every point of its domain. Alright, so there it is. Kind of ran out of space there. You can just write in its domain. Alright, let's take a look at our next fact here. Okay, let's talk about the Theorem 6 in the book here. Alright, properties of continuous functions. There are several things that are true for continuous functions. But before we talk about that, let's talk real quickly about what some continuous functions are. Okay, here are some polynomials, alright, exponentials, absolute value functions, rational functions. The one we just drew a minute ago was a rational function. It had an asymptote. We said it was continuous on its various pieces. We also have trig functions. As you know, tangent, cotangent, cosecant, secant have tons of asymptotes, but again, each branch is continuous in its own way, right? In its own right. So, and the root function. And I'm sure there were others. Logarithmics, for example. Okay. Here's the property. If f and g are continuous at x equals c, then the following are continuous at x equals c. Okay, f plus g, f minus g, f times g, f divided by g, assuming that g of c is not 0, because you couldn't divide by it, right? A constant times f, where k is any real number. These are all continuous as well. Okay. Theorem 7 says all compositions of continuous functions are also continuous. Alright, so why is that important? Alright, well here's why this is so important. You might be given a function and you're not sure if it's continuous or not. But if you look closely at it and you can find a way to decompose it into two continuous functions, then it must be continuous after all. So this is a way of recognizing whether a function is considered continuous or not. So of course we're going to do an example, because I don't know if you caught what I said. So let's go ahead and take a look at our first example here for that. Let's say that we're dealing with f of x. Stylus going crazy there. Okay. X sine x over x squared plus 2, all in absolute values. Okay. Well, first of all, x sine x and x squared plus 2 are all continuous functions of their own. So I'm looking at this as three parts. So this is x made up of an x. It's got a sine x multiplied in there, and there's an x squared plus 2. These are all continuous. Functions independently. How do I know that? Well, if you look up above, we said earlier this very thing. We said right here that all polynomials, so x is a polynomial, all trig functions, and all polynomials, x squared plus 2 is a polynomial, are continuous functions. Okay. Absolute value of x is also continuous. Notice there's an absolute value going on here. Now it's not absolute value of x, it's absolute value of some other things, but it is nonetheless a continuous function. It's also up here. Absolute value functions. Okay, so why is it, or is it, that this function we're looking at, f of x, is this thing continuous? Well, we should be able to decide that now. So let's take a look. It seems like everything it's made of, and everything that makes it up, is continuous. The parts are, and the entire expression being absolute value. So let's go ahead and work this out. Okay, so we know that since x is continuous, we know that x times sine x is continuous. So x times sine x is continuous. Right? That's because we said up here that a product of two continuous functions is continuous. Then we could say that x squared, if we divide by x squared plus 2, that would be continuous. And that's because if you take a function and divide by a continuous function other than 0, then you maintain continuity there. And lastly, if we call this r of x I cannot write with a stylus. We called r of x r of x equals x sine x over x squared plus 2. Let's let s of x be the absolute value function, which is continuous. So I guess you're just supposed to kind of go to the top of the page here and start erasing stuff. There we go. Yeah, there's a nice big eraser there. That's kind of cool. Yeah, I like that. That's neat. Which is also continuous. Yeah, good thing it is. If we compose S of R of X we still have a continuous function. Okay, so S of R of X is a composition of continuous functions into absolute value function, which is a continuous function. So here's your r of x stuck inside s of x. That's kind of hard to write. Okay. Okay, so s of r of x is indeed continuous. F of x is a continuous function. What a mess. Now, it's, again, it's not continuous because this denominator doesn't yield 0. In other words, it's not about the domain here. It has to do with more the fact that we were piecing together continuous stuff. All right. Theorem 8. The intermediate value theorem, also known as the IVT for continuous functions. Alright, so here's what the theorem states. It says a function that is continuous on a closed interval takes on every value between f of a and f of b. Okay, so let me write out the function here. Or I mean the theorem. A function that is continuous on a closed interval a to b takes on every value between f of a and f of b. What is that saying? Alright, here's what it's saying. Remember, this can be so known as AB. This is actually really neat theorem. Okay, let's say that you have a point here with coordinates a, f of a, and another point over here with coordinates b, f of b, and there's a curve connecting. All right, so let's just say it looks like this. Okay, so here's basically what it's saying. It's just saying that if the curve really is continuous between A and B, then it must be true that when the curve is drawn, that you pass through every possible y value between f of a and f of b. So this might be like 2 and 5, and this on the x-axis might be like 1 and 10. You don't have to write this down. Or let's just say that let's say this is 1 and 10, and let's say that this is 2 and 7 or something. 2 and 7. Still get used to this thing. It's okay, it's okay. let's do. Alright, so we're going to be traveling from this point to this point, and we're going to be passing along the curve. We're going to have to touch every possible y value between 2 and 7 if we're planning to travel from 1 to 10. Okay? And yeah, I challenge you to connect the two dots without passing through every possible y value from 2 to 7. You can't do it right, no matter how you connect. You can connect along this path. Right? You can do any path you want. But you're going to pass through every possible y value. So that's all that's saying. Pretty neat rule. It's common sense though. Alright, so let's look at how we might use this in a problem. Alright, I'm having trouble with the edges. Laugh if you wish. Is there any real number that is 1 less than its cube? Is there any real number that is 1 less than its cube? Can you think of a number that is 1 less than its cube? Remember, that would mean x to the third, that's its cube. 1 less than its cube, x cubed minus 1. Do you think there's a number that fits the mold here? Well, it isn't 1, because plugging in 1 here doesn't make a true statement. It's not 0. I wonder what it is. Okay, our goal is not really to find this number, but to see if there has to be a number. Okay, so what I'm going to do is I'm going to go ahead and move this x over to the other side. And I have 0 equals x cubed minus x minus 1. Alright. Okay, so I'm going to look for the x-intercepts of this function here. So let f of x equal x to the third minus x minus 1. And we will plot it. Okay, so I'm going to go up to the top here a little bit, use some space above. I think I can probably squeeze it in right in here. Okay. Let's make a little XY table here. Alright, so I plugged in -2 earlier and I got -7. And I plugged in -1 and I got -1. You can test this out. Plug in -1, I get, or 0, I get -1. Plug in 1, I get -1. If I plug in 2, I get 5. Okay, so let's plot that real quick. So left 2, 2, 3, 4, 5, 6, 7. There's that point. Oops. There's that point. There's this point. There's 1, -1. 3 in a row right there. How about that? And 2, 5. 1, 2, 3, 4, 5. Oops, except that I plotted -2, -7 wrong. I'll just make sure you're awake. Okay, so 3, 4, 5, 6, 7, some right about here. Okay, so the curve actually, I'll draw it in red, looks like this. Okay, see right there, I just crossed the x-axis in my attempts to go from this point here to this point here. So on this close interval, we have a polynomial function. Polynomial function. Polynomials are supposedly continuous. We said that if you're going to be going across from one point to another, you will be traversing through every possible y value. Since this is down at -7 and this is up at 5, the IVT is stating that there is, with 100% certainty, it's stating that we did pass through the y equals 0 mark, because that's one of the possible y values here. Okay, so this graph does pass through the x-axis. In other words, there is a time when this is true. This is true, according to IVT. Right. So where is it in here? I don't know. 1.152. I have no clue. That's not the point of the question. The point of the question is just to check for existence of this number. So that would be a fun problem to try. See if you can maybe use your trace button or something. See how accurately you can get that value. You can try it out. Just graph this thing, and you can also do the 0 feature on your graphing calculator. Find the 0. If you want to pursue it further. Okay, but that's all that I had for this lesson. So just make sure you take a moment and decide what you've want to memorize, or write down a few things you've learned. Try to use complete sentences again. That's important here, remember. Okay, until next time.